In section 9.1, we're going to look at sequences. Now, hopefully most of this will be a review from pre-calculus, because what you're going to see in this chapter is we're going to look at topics that we learned in algebra or trigonometry or wherever you learned it. It was in a pre-calculus class. And so we'll review some of that, but we'll see how to use calculus and how calculus fits in with these algebraic topics that we have learned in the past. Okay, so remember that a sequence is a function whose domain is the set of positive integers. So we usually denote it with a subscript rather than the function notation, even though it is a function. And when we use our graphing calculator, we're going to use what we call sequence mode to plot terms. So I'll show you how to do that. If this is a review for you, great, and if not, it's not too difficult to learn. Okay, so examples. In function notation, we would say f of 1, but in sequence notation, we say a sub 1, or we would say a of 1. But that just means the first term of the sequence, the same with the second term, the third term. So we don't usually use this function notation. We just use this subscript notation. So when we talk about the entire sequence, we put brackets around it and we say, just here's a generic term, a sub n. Okay. So here's our first example, a sub n is going to be the sequence 1 minus 1 over n. So if we wanted to write out these sequences, or write out the terms and see what the terms are, we would say if n is equal to 1, that would mean that a sub n, or a sub 1, is going to be 1 minus 1 over n, which happens to be 1, so we get 0, right? If n equals 2, that means a sub 2 would be 1 minus 1 half, which of course would be a half, and we would just keep going. A sub 3 would be 1 minus a third, so we would get 2/3, right? Which matches up with our first term, our second term, our third term, and it would just keep going. We can see that if n was 4, we'd have 1 minus a fourth, which is 3/4, like that. Okay. In example 2, we are looking at an alternating sequence. This -1 to the n power we know is going to alternate the sign, because -1 to an even power we know is positive and -1 to an odd power is negative. So now we want to look at our first term, and that gives us a 0. So look at what's happening. Well, it looks like we're going to start counting at 0, right? Because a sub 0 would be then -1 to the 0 power times 0. And -1 to the 0 power is positive 1, but 1 times 0, of course, is 0. And that gives us our 0 for our first term. We're just counting from 0 this time. N equals 1, that would give us a sub 1, and that would be -1 to the first power times 1, which would give us the -1 here. And let's try one more. If n is 2, then that means that a sub 2 is going to be -1 squared times 2. So the sign obviously alternates back to positive, and we get our 2. All right, so these are the things that you want to look at when you're dealing with a sequence. Sequences can start at really any value for n that you want it to. You just need to be aware, and that tells you what the domain of the sequence is. Sometimes, if we look at example 3, sequences are recursively defined, and that tells us that the nth term is determined by knowing the term before it. Okay, So here we see that if we want to get the n plus 1 term, we need to take the nth term, the term right before it, and subtract 5 from it. And this tells us that the first term is 25. So if we know the first term, we can get the second term by subtracting 5. So it's just going to be 25 minus 5, which is 20. Then if we want the third term, we take the second term and we subtract 5 from it. So the third term is going to give us 20, which is what we got from right here, minus 5, which is 15, and so on and so forth. Okay. But most of the sequences that we're going to be looking at in this chapter are sequences that have limiting values. And what that means is that as we count our n's, as they get higher numbers out toward infinity, the sequence, which would be considered the y value, the values of the sequence of our function tend to converge to a particular number. So what we're really concerned about, more so than if there's no convergence, so those values might go off to infinity, we want to look at sequences that tend to converge to a particular value. So if we look at example 4, we can see that the sequence defined as 1 over 2 to the n, these numbers are getting smaller and smaller and smaller. And eventually, we're going to have 1 over 64, 1 over 128. If we kept going on and on and on, that sequence is going to converge to 0. Those values, if we let n get big enough, are going to be really, really close to 0. So what we need is a definition to explain this to us. When do we know that a series converges to a value? Other than just looking at the sequence and trying to guess and say, well, logically, it looks like this should be going to 0. Each of these numbers is getting smaller and smaller and smaller. So what is small enough to decide that 0 is the value that the sequence converges to? Let's take a look at this definition to decide. So we have a limit. Okay, L is going to be what we are going to call the limit. The limit of a sequence, L, is written as the limit as n goes to infinity of a sub n is equal to L. Right? So just like limits that we did back in Calc 1 when we were learning about calculus, same thing. If for each epsilon greater than 0, this time there doesn't exist a delta, but there exists an m greater than 0, that whenever a sub n minus L, so the sequence value minus the limit, is less than that epsilon, that's going to happen whenever we get an n bigger than this m. So let's take a look. Here, we're going to choose, down here, we're going to choose our epsilon. Okay, that's the distance between L and L plus epsilon, that little bit right there. So we look at the interval from L minus epsilon to L plus epsilon, and that's shaded in blue through here. Okay, so if we look at the sequence, the values of the sequence are getting down here, and they seem to be all eventually getting into this blue area. And so if we look at the fifth term, so right here would be when n is equal to 5. Well, the a sub 5 would be that value right there. And then when a is equal to 6, or n is equal to 6, that would be a sub 6. Well, then a sub 6 is in that blue area, but then we look at a sub 7, and that pops back out of that area. So we can't have our m value there. But eventually, as we look at all these values for our sequence, once we hit right about here, those values are going to stay within that blue shaded region, and they're going to get closer and closer and closer to our value of L. So that's how we're going to say that L is our limit. Okay? So how do we go about finding a limit? Right? Here is what we're really looking for. We need to have a sequence, a sub n, and then we need to take the limit as n approaches infinity. So this would be, since if our function, our sequence is n plus 4 over n plus 1, what we really want is we want the limit as n approaches infinity of n plus 4 over n plus 1. And we know that if we multiply the top and the bottom by 1 over n, we're really just multiplying that fraction by 1. Same technique we used when we found the limits of functions when we first started learning calculus. And if we distribute that 1 over n through the numerator and distribute the 1 over n through the denominator, we're going to get n plus 1 times, or I'm sorry, 1 over n times n is going to be 1, plus, and then 4 times 1 over n, I'll just get 4 over n. And then in the denominator, n times 1 over n is going to be 1, plus 1 times 1 over n will be 1 over n. So we know as the n goes to infinity, 4 over n is going to go to 0, and 1 over n is going to go to 0. So that tells me that that limit is going to be 1 over 1, or 1. Okay? So what that means is that this sequence converges to 1. So now what we want to do is we want to look at how to use this, how to put this into your calculator so you can get that limit and you can see the sequence in the calculator.